The next topic that we want to look at in our study of functions is that of the inverse function. And before we really look at the inverse, we need to remind ourselves about the definition of a function. Remember, a function is a rule of correspondence in which each element in the input is assigned to exactly one element in the output. And the input, remember, is the domain. The output, remember, is the range. And that's a very important thing to remember, this idea that each element in the input corresponds to exactly one element in the output. So you never have an element in the input corresponding to more than one element in the output. That's important to remember, because if you have a situation, a relationship where an element in the input corresponds to more than one element in the output, that is not a function. That relationship is not a function. Okay, so let's look at a couple of functions here. Of course, these are just polynomials. F of x equals x squared and h of x equals x cubed. Now, these are very similar functions in that they're both polynomials, they're both power functions, but they have an important difference that's going to be pertinent in our conversation about inverse functions. Now, first of all, I want to just generate some inputs and outputs for these two functions. I'm going to use for both functions the inputs -2, -1, 0, 1, and 2. And you notice we get the corresponding outputs. Now, what I want to look at first of all is this function f of x equals x squared, because this is definitely a function, but I want to explore it. And now, of course, here's the graph. I want to explore this idea. What happens if we were to interchange the ordered pairs so that the x's all became y's and the y's would all become x's? We would get a different relationship there, and what I'm wondering about is, would that relationship be a function? Well, let's see. Let me make that swap. Now you notice that all of these y's have become the x's in this new relationship, and all of these x's have become the corresponding y. So what we've done is we've just interchanged the x and y's in all the ordered pairs. Now, here's what I want to take note of. Notice that this 4 and this 4, correspond to different numbers. 4 corresponds to -2 here, but down here it corresponds to a +2. And notice how that would appear on this graph of f of x equals x squared. Notice that I drew this horizontal line here, which illustrates that, yeah, 4, notice this relationship here. This 4 corresponds to this 2, and up here the 4 corresponds to a -2. So when we swap the ordered pairs, we notice that, first of all, we don't have a function here, right? Because the 4 corresponds to -2 and the 4 corresponds to 2. That also is the case for the 1's. So what we want to take note of here is that, first of all, when we swap the ordered pairs, we don't have a function. We have a relationship, but it's not a function. And how that is manifested by looking at our original graph is, if we look at the graph of x squared, we notice that this function is we say it's not 1-to-1. It's not 1-to-1 because, yes, the every x corresponds to exactly one y, but every y does not correspond to exactly one x. So it's not a 1-to-1 function, and it's made clear by these horizontal lines. If you can draw a horizontal line any place on the graph that touches the graph more than one time, then we say that function is not 1-to-1. And we say that it fails the horizontal line test, and this function does not have an inverse unless we restrict the domain. But on the regular domain, if we have f of x equals x squared on the natural domain, -infinity to infinity, there's no inverse existing. Now, of course, this function might be 1-to-1 if we only looked at maybe 0 to infinity, where we didn't have this part to the left. But the purpose here is just to illustrate why we would say f of x equals x squared does not have an inverse function on its domain from negative infinity to infinity. Now, let's take a look at this one in contrast, f of x equals x cubed. Here's the graph, and you can see that if we tried to draw a horizontal line any place on this graph, it would touch the graph at most once. In fact, exactly once. Every horizontal line we draw. Now let's see if we swap the ordered pairs again like we did on the other one and make the y's the x's and the x's the y's, we see that we do have a function here. Every x corresponds to exactly one y. So we would say that h of x equals x cubed is has an inverse. When we swap the ordered pairs, we do get a function. And that corresponds to the fact that this graph is a one-to-one graph. Or h of x equals x cubed is 1 to 1. Now, notice that when we talk about inverse functions, what we're talking about is what happens if you interchange the x and the y. Well, when you do that, do you then get a function? In other words, is the relationship still a function when you swap the ordered pairs? But to be a little more rigorous, I've included the definition of the inverse function. Let f be a one-to-one function. Then the inverse function of f is the function whose rule is g of y equals x exactly when f of x equals y. The domain of g is the range of f, and the range of g is the domain of f. So see, you get the idea that everything is being swapped. All the ordered pairs on the function f, if you reverse all of those and make the y's x's and the x's y's, those will be ordered pairs on its inverse. Now let's see what this looks like graphically. We're going to consider f of x equals x squared. We've already concluded that that function has an inverse. So let's just plot some points that we generated earlier. We've got 2, 8. That's on that. That's a, f of 2 equals 8. We've got 1, 1, 0, 0, negative 1, 1, and negative 2, 8. All of these are points on that graph of f of x equals x cubed. Now, I'm going to swap the ordered pairs so that we're going to take this point, which is 2, 8, and I'm going to make it 8, 2. And I'll plot that in yellow. And I'll do the same thing for negative 2, negative 8. I'll plot negative 8, negative 2. And then notice each one of these points, negative 1, 1, 0, 0, and 1, 1, it doesn't matter if I swap those ordered pairs, I'm still going to get the same point. Now, what we want to note here is that these points that I've plotted have symmetry to the original points about the line y equals x. So notice, this point 2, 8, notice the y equals x, and the point 8, 2, these have symmetry across this line y equals x. So that if this grid here were on a piece of paper, and I were to crease the piece of paper along this y equals x, and fold it along that line y equals x, then this yellow 8, 2 would fit perfectly on top of the blue 2, 8. And likewise, the 2, negative 8 would fit perfectly on the yellow negative 8, negative 2. So that's why we say that these graphs have symmetry. Now notice I've went ahead and included the graph. I've got y equals x. Here's y equals x cubed, the blue. And then the yellow, of course, is the inverse graph. And notice that these graphs have, just looking at it, you can tell that they're symmetric about the y-axis. About the y equals x. Okay, so we note that about inverses. Now, Some other things we want to take note of, what's referred to many times as the Round-Trip Theorem. And here we have that if you take f of g of x, where f and g are inverses, you have f of g of x equals x. Now, notice, I'll just read this. For all x in the domain of g, and let's go the other way, g of f of x equals x for all x in the domain of f. Now, this happens, f of g of x equals x and g of f of x equals x, only when f is 1 to 1 and g is its inverse. So in other words, if you have two functions, f and g, and you want to know, are these inverses? Well, calculate f of g of x and g of f of x. If both of those equal x, then yes, f and g are inverses of each other. Now let's illustrate the round-trip theorem. Here we have f of x equals x cubed and g of x equals x to the 1/3. Now, let's go ahead and calculate f of g of x. And of course, we're going to take something and cube it. And what we're going to take is g of x. Now, using our exponent rules, we have x to the 1/3 times 3, which equals x. Now we go the other way. G of f of x equals blank to the 1/3, so that we put in the x cubed, and that also turns out to be x. So this is an illustration of this round-trip theorem. Okay, now let's look at, well, how would one find an inverse function? Let's consider this function, f of x equals x cubed minus 5. And of course, we know this is a 1-to-1 function by looking at the graph. It's the x cubed function, only shifted down 5 units. So clearly it's 1-to-1. We've already established that. Now here's the process for finding the inverse. First of all, I want to change notation. I want to get away from this f of x and use y, because we're about to do some algebraic manipulations here, and that f of x gets kind of cumbersome. Now, next we want to interchange the variables. Notice, when we talk about inverses, remember we change the x's, interchange the x's and y's, and that's what I've done here. In place of the x cubed, I've got y cubed. In place of the y, I've got x. Now, we want to solve. So we change, interchange, and solve. Okay, so I need to add 5 to both sides, and then take the cube root, and now I have y equals the cube root of x plus 5, and then I change notation back. So notice we changed, interchanged, solve, and then change back. And now we have our inverse function.